Hey, math nerds, how's it going? So in this particular video, I'm going to do Leibniz rule. So this is basically when can you say or when can you do this particular step where the derivative, you can take the derivative inside the integral. So you have an integral of some function of a two-valued function, and you're integrating with respect to the first variable. And so there's this second variable here. So you can integrate the whole, you can differentiate the whole integral with respect to the second variable. And then you can basically take the derivative inside the integral. So this is called Leibniz rule. So the question is, when can you do this? So this can be done, and it's called Leibniz rule. So I'll be giving you the statement and the proof of this particular theorem here. So, okay, this is a big statement. You don't have to be afraid of this. So there is a function phi, which is defined on this rectangle here, ABCD. So which is basically this particular rectangle AB and CD on this XY plane, and it's complex valued. So I'm taking complex numbers here. So basically the range is complex numbers, okay? All right. And this function is basically given as continuous. So it's a continuous function. And now I'm defining this particular function gt, which is basically the integral of this function phi. Then the statement says that g is continuous. And moreover, if it's given that this particular partial derivative of this function phi with respect to t, which is basically its second variable, if that is continuous on this particular rectangle ABCD, AB times CD, then you can take the derivative inside the integral. And so g prime t is basically given like this. So it's integral a to b partial of phi with respect to t ds, okay? Okay, so the gist of this theorem is when you have the partial derivative with respect to t is continuous, then you can take the derivative inside the integral, okay? Now I'll prove this. So this video will be in many parts, and let's go step by step. So first I need to prove that this particular function gt defined to be integral a to b phi of st ds, I need to prove that this is continuous, right? So this needs to be continuous. So how can we do this? Well, it's given that the function phi is basically, it's defined on this rectangle AB times CD, and its range is complex numbers, right? Now, so we need this, this is what we need, and it's given that the function phi is continuous. Now, this particular domain, it's called as compact, okay? It's a compact set. Compact set means that it can be, if you cover this set with any number of open sets, if you know what that means, then this compact set can be covered by a finite number of those open sets. Among all those collections, you can pick finite number of them and you can cover it, okay? Well, if you don't know compact sets, what they are, it's perfectly fine, but this is a compact set, and continuous functions on compact sets are uniformly continuous. So this is uniformly continuous. Okay, I will define what is uniformly continuous, right? So basically, uniform continuity means that if you have an epsilon, or for an epsilon, there exists a delta, okay, which depends on epsilon, such that if you pick any 2 points, let's say s prime t prime and s and t in this particular domain, which is a rectangle, if you pick any 2 points, and if the distance is less than delta epsilon, then what you have is the distance between the function values at these 2 points is basically less than epsilon, okay? This is what is happening here. So if you pick 2 points whose distance is less than delta, then the function value at those 2 points will be bounded by epsilon. Okay, so that is uniformly continuous. See, I can pick any 2 points. It doesn't matter which 2 points I pick, but if the distance is less than delta, this happens. That's the key thing in uniform continuity. Okay, so that's uniformly continuous. Now, what I will do here is that, in particular, I can pick points, wisely. By that I mean, maybe I can fix this S, right? I can fix the S and maybe pick 2 points, maybe different only in the second variable, right? So maybe t prime and t. So if you take the difference of this, so basically you need to calculate the distance. That's basically s minus s square plus t prime minus t square and then square root. Because s and s, it's the same thing, it's 0. So this is basically t prime minus t. Okay, so this distance is absolute value of t prime minus t. Now, let's say this is less than delta epsilon. Okay, that means these 2 points with fixed s, if they differ by delta epsilon, then what we have is that phi at st prime and phi at st, they differ by epsilon, right? Because the distance between those 2 points is less than delta, so this should differ by epsilon. Now what I'm going to do is that I'm going to integrate phi st prime ds, and then I'm going to integrate phi st ds, and then I'm going to take the absolute value. Okay, so what is this? Well, you can group them. So phi st prime minus phi st ds, and then what happens is that your absolute value goes inside the integral. Okay, and then this is ds, and now we know that this is bounded above by epsilon because t prime and t is less than delta, right? So this here, t prime and t, they differ by delta epsilon. So this is bounded above by epsilon times integral a to b ds, which is basically epsilon times b minus a. So what do we have here? So if you pick t prime and t, which differ by delta epsilon, then what we have is that this particular integral here, which we had defined before, it's g of t prime, and this is g of t, they differ by epsilon times b minus a. So in particular, if I choose epsilon to start off with, if I had chosen epsilon to be, the maybe epsilon prime is epsilon divided by b minus a, okay? If I had chosen like this, then here what we'll have is basically epsilon prime, right? And which is basically epsilon divided by b minus a, and then there's a b minus a here, and they get cancelled. And so this quantity, absolute value of gt prime minus gt, this is bounded above by epsilon. So what we have here is that if you pick t prime minus t, which is less than delta epsilon, then g of t prime minus g of t, that's bounded above by epsilon. Okay, so that's exactly is the definition of continuity. So this implies that g of t is continuous.